Welcome, ladies and gentlemen. Please be ready to share your response for this morning's Bellwork when I call on you. So y has a local max when y prime switches from what to what? Right, so y would have a local max if y prime switched from what to what? Tyler?
Positive and negative.
Positive to negative. Good. We know a positive sign on y prime indicates increasing behavior on y. Negative values of y prime indicate decreasing behavior on y. Therefore, we must have a local maximum when y prime switches from positive to negative. Awesome. And we'll be using our sign charts then to help with that analysis. Go ahead and raise your hand if you had the same as Tyler. Positive to negative. Awesome. Absolute extrema may occur at blank, and we've got a couple different possibilities. And so one place that absolute extrema could occur are, Riley E?
Endpoints.
Endpoints. And so absolute extrema could occur at the endpoints of a specified interval. Endpoints, or what's our other option for that? Maggie?
Critical value?
Yeah, critical values. Or critical points is this text called. We call them critical values. So if we have an absolute maximum on a given interval, then it must occur at a critical value or at an endpoint of the interval. The same is true for an absolute minimum. So we're going to use this as part of our analysis, especially next class period. And lastly, thank you. And lastly, number 3, y has an inflection point when y double prime switches what? And so in order to have an inflection point on y, we remember that's a change in curvature, then y double prime switches what? Kobe?
Signs.
Yes, it must switch signs. It must switch from positive to negative or from negative to positive, but there must be a sign change. It's not enough for y double prime to equal 0 or be undefined at a particular x equals c value. That doesn't guarantee the existence of a point of inflection. It just gives us a possible point of inflection. We still need to further investigate, right, to see if y double prime changes sign. So that's going to be kind of our mantra today. We can generate potential places where y has an extreme. Right, we can generate potential places where y has a point of inflection or may have a point of inflection, but then we have to go and do the analysis with the sign chart in order to verify that y prime or y double prime changes sign. That's going to indicate the actual presence, and we'll use that when we graph analytically. Awesome work, you guys. Thanks for your help. What questions do you have about your Bellwork? Okay, so now we're going to go ahead and hold off on our derivative review for the B-Day classes as a result of the ACT administration. They haven't gotten that yet. They're going to get that during their cycle this time with day 2. And so hang on to your derivative review. Please don't turn that in. Your derivative review is going to be part of OTL number 2. It'll be turned in next time, and I'm hopeful that you're able to use that class time from last A-Day in order to get a lot of it done. Instead, what we're going to do is turn in our OTL number 1, and staple the half sheet to it. This is from way back on Monday's class period, and then we're going to go ahead and give yourself credit for those that you completed out of 33. If you'd like to start the stapler around on this side, that'd be awesome. Thanks, you guys. Out of 33. And I'll go ahead and pause the recording while we take care of this. Okay. So, quick reminder, right? This is something that we ran into on our test. We want to make sure that we're selecting and using the appropriate antiderivative rule, right, when encountered with an indefinite integral. So we saw lots of different things on your Unit 7 test. Is the indefinite integral of 1 over y squared, right, with respect to y, is this overall natural log rule? Natural log. No. Is it overall an inverse tangent rule? No. Overall, what antiderivative rule would I use to integrate this? Hayden?
Power rule.
Power rule. We know that for natural log, I must have a quantity on the bottom raised to the first power, right? And the derivative of that quantity must be present. As I look at this indefinite integral's integrand, 1 over y squared, that's to the second power. Inverse tangent, I would need that sum on the bottom, 1 plus y squared, not just y squared by itself. And for power rule, it looks like we're all set to go. I can interpret that as a y to the negative 2 as the current exponent. Adding 1 to the current exponent gets me y to the negative 1. Dividing by the new exponent gets me negative 1 over y. So guys, we should have all had this, right? Opposite of 1 over y plus the on our test for this derivative, and it did show up a couple different times. All right, so this is power rule, and I'll go ahead and for our notes. Awesome. Okay, so today we're going to graph with calculus, and we're not going to use our graphing calculators until the end to check. Recorded and plugged in the USB port, so we can't hear the balloons, but we felt them, didn't we? Did you guys feel that? That was pretty cool. All right, so we're going to use strictly analytic methods, and I want you to know, I don't want you to get hung up on the quantitative, right? The quantitative values of like zeros of the function, where exactly we cross the x-axis, or where exactly we have maximum, well, maximum minimum we're going to find where exactly we cross the y-axis necessarily. What I want you to focus on is the qualitative behavior. That is, where are we increasing, where are we decreasing, where are we changing curvature, and so we're all about local extrema, absolute extrema, and points of inflection today using our first and second derivatives, and that's where we're headed. All right, so let's go ahead and find our note sheet for day 2. We're going to start with an easy one that we could already create using methods that we developed back in FST and pre-calculus, and so we could get a pretty darn accurate graph of this if we just continued to pick x value inputs, more and more of them, evaluating the function over and over again, or my first formal observation, over and over again, and then plot all of them together, and we see a cubic function, right? We can already interpret that as our down-up end behavior, our disco end behavior, so we know what this looks like. I want to start with this one because of that. We know what this looks like, so we're going to use this one as an easy one to generate the scheme, and then we're going to take a look at some more complicated ones, some transcendental ones, or some radical functions that we're not as familiar with. Awesome. So we're going to be able to answer questions like, on what intervals is y increasing versus decreasing? Where does y have relative extrema? And lastly, on what intervals is y concave up or concave down, and then we'll sketch a graph. So let's go ahead and tackle the increasing versus decreasing. What derivative tells me about increasing versus decreasing behavior? Michael?
Can you repeat it then?
What derivative of a function y tells me about y's increasing versus decreasing behavior? The first derivative or the second derivative?
The first derivative?
Absolutely. The first derivative, y prime, tells me about a function's increasing versus decreasing behavior. So to analyze that without using our grapher, we're going to go ahead and find y prime and make a sign chart for that. So everybody, let's go ahead and generate y prime. Based on our original function y, we'll differentiate term by term. Go ahead and share your derivative term by term. Colin?
Y prime equals 3x squared.
3x squared minus 3. Awesome. Thank you. We know, right? We know that the only places that y could change direction are at critical points. And so what we're going to do is find those critical points, those critical values, those x values where y could change direction by considering the two possibilities that lend to critical points. That is when y prime equals 0 or when y prime is undefined. Every time, right? That's going to be part of our analysis. And so I'll scan y prime and I'll say, are there any values of x that make y prime undefined? No, y prime is a tiny little parabola, right? A quadratic polynomial, and so there's no values of x that make it undefined. Will it ever equal 0? Well, yes, it looks like it will equal 0. Let's go ahead and find those x values that do so. Those are my critical values, and I'm going to use those in my analysis with my sign chart. Here we go. 3x squared minus 3 equals 0. Does that ever happen? Well, factoring is going to be our friend when we do this analytically. I'm going to factor out a 3 GCF, greatest common factor from each term, and rewrite in fully factored form x squared minus 1. I'm going to keep the party going because I love the difference of perfect squares. And I'm getting x plus 1 times x minus 1. Yes? And so it looks like we have critical values, right? We have critical values when y prime equals 0 and y prime is undefined. For us, we've got critical values at x equals, it looks like negative 1, and at x equals positive 1. X equals negative 1 and x equals positive 1 are the x values, right, the critical values, that I'm going to put on a number line and create a sign diagrams chart, just like you did for your prerequisite OTL. That will lend into our analysis of the original y increasing or decreasing behavior. So here we go. Let's go and make a sign chart. You must label your sign chart. 4 points on your Unit 8 test, right? We want to label this so that we know what it is we're analyzing. So I know that my y prime sign chart is going to tell me about increasing behavior of y. So I'm going to label this as my y prime sign diagram. I'm going to put on it the x values that are my critical values. They're negative 1 and negative 2. I'm sorry, -1 and +1. Those are my x values. And I don't need to include any other x values on my y prime number line. How come? Because those critical values are the only places where y could change direction. Therefore, they're the only possible turning points of my original graph. They're the only x values I need to include on my y prime number line. Let's go ahead and perform now our analysis with sines. So I'm going to choose a convenient x value on each subinterval, evaluate y prime, and see what sign it is, positive versus negative. And I'll use that to answer the original question, because you guys already know from first semester and last year that when y prime is positive, y is increasing, and when y prime is negative, y is decreasing. So here we go. What's a convenient x value to the left of -1? Riley? -2. I'm going to go ahead and take -2 and plug it into any y prime form. I like to go in my fully factored form when I'm doing an analysis of sine charts. So I'll go to my fully factored form because that's easiest for me. If I plug in -2 for x, 3 is positive. -2 in for x would make this negative. Times -2 in for x would make this last factor negative. So negative times negative overall is positive. It looks like y prime has positive values in the interval -infinity to -1. What's a convenient x value on this next subinterval? Hanukkah?
0.
I'm down. Let's go ahead and plug 0 into my y prime expression. 0 plugged in for x in any of my y prime forms, right, is going to produce 0 minus is negative. I'm getting a negative value of y prime. Can we put that in the fully factored form? Certainly. If I plug in 0 for x, I get positive times negative overall. An odd number of negatives results in a negative value of the expression. So I'm getting negative y prime values on my subinterval -1 to 1. Yes? Convenient x value in my last subinterval, Aiden? 2. Let's pick 2. This makes positive times positive overall. 3 positives, all positives. That means y prime has positive values on that right subinterval 1 to infinity. Awesome. Now we're ready to answer the original question that was asked. Y prime tells me exactly about increasing versus decreasing behavior of y. It looks to me like y is increasing on, looks like -infinity. That always gets we'll use interval notation for the sake of efficiency. -infinity always gets the parentheses because it's not a particular value. So -infinity up until -1. I'm also going to include parentheses on the -1 because at -1, y is not increasing. Y prime equals 0 there, so y must have a horizontal tangent. So therefore, I'm not going to include -1 on my intervals of increasing either, and I'll show that with the parenthesis and interval notation. Union, it's also increasing on parenthesis 1 to infinity. And so we see that, given our sign diagram chart. If this is a free response question, then we have to say why our sign diagram will not be sufficient justification. We have to go on to say, because y prime is positive on those intervals. So we have to go ahead and state specifically that y prime is positive. We can't assume that the grader is going to go look up there and see that and know that you know that that's the case. So you have to say because y prime is positive. That's the point. Y is increasing when y prime is positive. Great. And y is decreasing. Y is decreasing. Y is decreasing on, and it looks like just that interval -1 to 1. Those are the only possible places, these critical values, where y could change direction. Therefore, our only possible interval where y is decreasing is on -1 to 1. And then if this is on a free response question, we have to go and include the justification because y prime is negative on those intervals. Awesome. What questions do you have about our first question, increasing versus decreasing? Great. Then let's go ahead and see where y has relative extreme. Remember, also synonymous, relative is synonymous with local. So local is another descriptor for relative extreme. Okay, so we can go ahead and import our y prime chart. I'm just going to rewrite this so we have it here. We wouldn't have to make a new one. I'm just going to go ahead and relabel that. We had our x values from -1 and 1. We had our increasing, decreasing, increasing behavior of y. Okay, so what we're going to do for our relative extreme is we can see that we have relative extrema when y switches from increasing to decreasing or decreasing to increasing. Therefore, y prime would switch from positive to negative or negative to positive. In other words, y prime has to change sign in order for y to have relative extrema. And so are there any places where y changes sign? I'm sorry, where y prime changes sign? Yes. Y prime changes sign at x equals -1 and at x equals 1. Both of those contribute to local extrema. And so y has a local, looks like what the feature would be at x equals -1, a max or a min. Maximum from Bellwork, we switch from positive to negative. Y prime means that y switches from increasing to decreasing, indicating y has a local maximum at x equals 1 because y prime switches from positive to negative.
Is that -1? X equals -1.
Yes, thank you, whole time. X equals -1 because y prime switches from positive to negative. Good. This asks where they have local extrema, not what they are. So that's a very different question. Here we're just stating the x values where they occur, right? As opposed to what those values are. Local extremum are y values, right? Local extrema are y values. All right, so what else can we say? Well, we can say y has a local minimum at x equals +1. Thank you, Michael, because y prime switches from negative to positive. Awesome. Can't wait. On what intervals is y concave up versus concave down? Which derivative tells me about the concavity of y? Marissa?
Quick points.
Which derivative tells me about the concavity of y?
Is it double prime?
The second derivative, y double prime, tells me about the concavity or the curvature of my original function y. And so Colin already told us my y prime is 3x squared minus 3. Go ahead and tell the class y double prime when I call on you. Maybe? 6x? Awesome. And so our y double prime function is just 6x. Y has possible points of inflection when y double prime equals 0 or when y double prime is undefined. The same is for y prime critical values for y, but now for possible points of inflection. Are there any values of x for which y double prime is undefined? No, we've got a nice linear function here, no problems with domain. So y double prime is never undefined. We don't need to include those on our y double prime number chart. However, it may equal 0. We can set equal to 0 and solve, and I see that we have a possible point of inflection. Possible point of inflection. Remember, it warrants further investigation at x equals 0 because y double prime equals 0 at x equals 0. So in order to determine whether or not we have a possible point of inflection, an actual point of inflection, we're going to go ahead and construct a number line just as we did before. So this time, we're making a y double prime number line. We'll label it as such. This is my y double prime number line. We must label that. On it, I'll include the x values of possible points of inflection. Again, those come from y double prime equaling 0 or being undefined. I have one such value, 0. That's it. That's the only thing I need to include on it. The only place that y could change curvature is when y double prime equals 0 or is undefined. And I have a single value, so I don't have to investigate any other values on there, no other intervals. Let's pick a convenient value to the left of x equals 0. Right? What's a convenient x value to the left of that? Kyle? -1, good. Into my expression y double prime. All right, that's reminding me because I've labeled it already. Looks like 6 times -1 is overall negative. So y double prime takes on negative values everywhere to the left of x equals 0. Convenient x value to the right of x equals 0. Courtney?
1.
1. Let's plug in 1 to y double prime's expression. 6 times 1 is 6 is positive. So y double prime has positive values everywhere to the right of x equals 0. Just by looking at my y double prime number line, I can now determine, right, the intervals of concavity. It looks like y is concave down on negative infinity to 0 because y double prime is negative on that interval. So let's go ahead and answer the original question. Y is concave down on negative infinity till 0 because y double prime is negative on that interval. We're going to save time and use an equality notation. And y is, I'm going to hold off on this too. Y is concave up on 0 to infinity because y double prime is positive on that interval. Everybody good? Okay. We're finally ready to put our analysis together and make an accurate sketch. Again, we're doing this qualitatively, so I don't want you to get hung up on actual, right? Actual y values, x values rather of the zeros, and actual y values necessarily along the way, except for our key points like local extremum that we've already determined. Okay, and so let's go ahead and make an xy t-chart. We're going to label our local max, our local min on it, our point of inflection, right? And we're going to do that labeling on our t-chart, and then we're going to go ahead and see if we can't construct a graph analytically. Then we'll check with our graphers on the same window and see how we did, okay? So here we go. We're going to go ahead and put our critical values on here and one on each subinterval, so I'm going to leave a little space. We had critical values and local extremes at, what? -1 and 1. We had point of inflection at x equals 0, so we need to include that. And then I'm going to pick one on either side. So I'm going to go -1. I'm going to go -1, 0, 1. And let's see if we can't include an x value on either side of those just to get a little bit better picture. -2 and 2. I think this will be sufficient. Okay, here we go. -2 in 4x in my original. -2 cubed is -8. Plus 6 is -2. Plus 4 is 2. I'm getting -2, 2. Check and make sure we're doing this non-calculator. We're staying strong till the end. -1 in 4x is -1. Plus 3 is 2. Plus 4 is 6. 0 in 4x, I got it, is paired with the y value output of 4. 1 in for x, 1 cubed is 1 minus 3 is -2 plus 4 is 2. And lastly, 2 cubed is 8 minus 6 is 2 plus 4 is 6. Take a minute and make sure you get the same values. I was never good with numbers, so bad things start to happen when I'm doing math in my head, Jake. All right, let's go ahead and label our key points before we make a picture. Which of these contributed to local extrema? Well, we had local extrema. At x equals -1, we have a local max. So the local maximum must be 6. That is a y value. So 6 here is a local maximum. At x equals 1, we had a local minimum. The local minimum is 2. It's a y value. The least function value attained on that arbitrarily small given window surrounding x equals 1. And that's a local minimum. And what other key point did we have? We saw that y double prime changed signs at x equals 0, therefore that's what feature on y? A point of inflection, or inflection point. So it looks like, well, that whole point, I should say, 0, 4. I'll just put an arrow to it. Is an inflection point. 0, 4 is an inflection point. Or point of inflection. Okay. Awesome. Can we put it all together? Yes, we can. So here we go. -2, 2. -1, 6. 0, 4. 1, 2. 2, 6. Oh gosh. we need a local max at x equals -1, so that's the top of a peak. We need a local min at x equals 1, so this is the bottom of a valley. We need a point of inflection at 0, 4, so I'm going to do that with a little X there. I'm trying to show the viewer that this is where I mean to change curvature. I need concave down before and concave up, so I need an upside down bowl shape before x equals 0. And right side up bowl shape, I'm changing curvature right there. And do I have concave down before and concave up after x equals 0? Yes? Okay, let's go ahead and check with our graphers. The moment we've all been waiting for, I know I have. Let's go ahead and change our window to the same so we can get an accurate picture. So we're going -6 to 6, guys, for our x values. And it looks like -6 to 6 for our y values. I'll go ahead and enter my original function, x cubed minus 3x plus 4 I'll give you guys a minute. Yes, yes, -6 to 6. Okay. The anticipation's killing me, bless you. And let's see how we did. Coming up. Oh, and even the blue line style. And down and OMG, KAT BFF. How do we do? All right, we didn't extend that down below. We weren't certain about the exact value of the 0, right? Because we weren't doing that. But it looks like we did pretty well. I know some of you right now might be wondering, what? I know I'm down with BFF, right? I'm wondering, pray tell, what KIT might stand for. To which I reply, keep in touch. You know, like in the yearbook, stay sweet, you know, in the summer. Stay sweet, KIT. Keep in touch. You'll catch on. Maybe on the yearbook sign. All right, ladies and gentlemen, so while we just did a polynomial, I think we're going to skip over this next polynomial, this quartic function, because polynomials, you already have a good intuitive understanding of what they look like, and you're familiar with them. Instead, let's go right on to something, a transcendental function. Everybody please find y equals e to the x minus 1 minus x. Again, we're going to perform a non-calculator analysis of this. Right? We're not going to use the grapher at all until the very end and see how we did. Again, we'll do qualitatively, so don't get hung up on exact values necessarily of the zeros or x-intercepts of the function. What we want to do is make sure that we're using calculus to find those qualitative things like the turning point, local extrema, maximum, minimum, right? Or the intervals of concavity and curvature, and we're going to do that all non-calculated. So here we go. Which derivative tells me about increasing versus decreasing, Kobe?
First derivative.
First derivative, everybody, let's find the first derivative of my original function y, e to the x minus 1 minus x. So I know the derivative of term by term, an exponential function looks like e to the x minus 1. The derivative of an exponential function is the exponential function itself. So that's e to the x minus 1 times the derivative of the exponent. Well, that would just be 1. Times the natural log of the base. In this case, the base e exponential, natural log of e is just 1 as well. So I've successfully differentiated the first term, that's good news. And now the second term, minus x, differentiates to minus 1. And so it looks like my y prime expression is e to the x minus 1, closed exponent, and then down on the ground floor, minus 1. Are you guys down? Did I do that right? Great. We now determine the critical values. Again, the critical values are the only places where y could change behavior, switch direction, right? So that's all I need to consider when I'm determining the intervals of increasing versus decreasing behavior. So what do? Well, I consider two cases. Is y prime undefined ever, and is y prime equals 0 ever? Those are the two situations that would give critical points on y. So here we go. I ask myself the question, for what values of x is y prime undefined? Well, this is an exponential function, and if I think back to my parent exponential function, base e to the x, right, is smooth and well behaved for all input values of x, and so there's no domain issues. Would change my exponent to x minus 1 affect its domain? No, it wouldn't. It would just be a step to the right 1 unit, and so that's not going to do anything with being undefined. Minus 1 at the end, is that going to do anything to the domain? No, that's just going to be vertical translation down 1 unit, and so it appears to me that there's no x values for which y prime is undefined. So there's no critical values that result from y prime being undefined. Are there any x values where y prime equals 0? I don't know. Let's set it equal to 0 and see. So I'll set y prime equal to 0 and solve and see if there's any x values that produce a value of 0 for y prime. Those are critical values as well. Those are possible turning points on my original y. Again, strictly non-calculated. Let's do it. So what would I do to solve this equation? I'll go ahead and isolate the exponential by adding over 1. E to the x minus 1 is equal to 1. How do I get a variable expression down out of the exponent and on the ground floor where I can solve for it, Marissa? Natural log, comma, maybe. Wonderful. So I'll take the natural log of both sides. Natural log of equals natural log of. We're taking the natural log of e to the x minus 1 and the natural log of 1. On the left-hand side, as many of you have justified, ln of e to the something is just a something. So, right, this becomes x minus 1 on the left. Whether you bring the log of a power property and bring that exponent down and then take the natural log of e as just 1, or you undo the base e exponential with the inverse properties of logarithms and exponentials of the same base. And then ln of 1 is equal to what?
0.
ln of 1 is 0. Good. And so it looks to me like solving for x gives me x equals 1. So I have a critical point at x equals 1, and that's a critical value that I'll place on my number line. So I got critical value at x equals 1. So here we go. Let's go ahead and make my number line. And what are we going to label it? Well, increasing, decreasing behavior on y is determined by y prime. So I'm making a y prime number line. I'll go ahead and put my critical values on there. It looks like my only critical value is x equals 1. So I only need to include one x value on my y prime number line. Let's perform a sign analysis of y prime. What's a convenient x value to the left of 1? Right? Evie?
Negative 2.
Negative 2?
0.
Let's do 0. 0 might be easier to evaluate. So let's see. 0 into y prime. Where do I want to go for my y prime expression? I'm going to go right to my original y prime that I differentiated. So I'm going to go ahead and go and plug in 0, right? I'm going to plug in 0 in for x and see what sign is produced by y prime. So if I plug in 0 here, I will get 0 minus 1 is negative 1. E to the negative 1 is 1 over e. Minus 1. 1 over e, right, is about 1 over 2.7. So that's about 1/3, right? 1/3 minus 1. Is that overall positive or negative? 1/3 minus 1 would be in the negative range. So it looks like y prime has negative values to the left of x equals 1. Thank you. What's a convenient x value to the right of 1? Emily?
2.
2. So let's choose 2 and see what happens. When I plug in 2 into my y prime expression for x and work it out, I get e to the 2 minus 1 is 1, so e to the first minus 1. And e to the first is 2.718, yes, about. So 2.7 something minus 1 overall is positive or negative? Positive, and we did it without a calculator. That's pretty cool. So what have we found? It looks like y must be decreasing on negative infinity to 1 because y prime is negative on that same interval, and y must be increasing on 1 to infinity because y prime is positive on that interval. So let's go ahead and state that. And now, in the interest of time, I'm going to do this smooth operator abbreviation. Y is decreasing on, what is it? Negative infinity to 1 because y prime is negative and y is increasing on 1 to infinity because y prime is positive on that interval. You guys good? Next up, where does y have relative extrema? Where does y have relative extrema? Well, y has relative extrema, right? When y prime does what? Changes sign. Are there any x values for which y prime changes sign? Yes, y prime changes sign at x equals 1, so I must have a local extreme there. It looks like I have a local minimum there because we switched from decreasing to increasing on y, indicating a local minimum value, so long as y is defined there. So here we go. Looks like y has, should I import? So this is my y prime number line with a single critical value at x equals 1. So I have negative, positive, yep, negative, positive. So I'm just, you don't have to remake this each time. I'm just importing that so that I can look at that. Looks like y has a local minimum at x equals 1 because y prime switched from negative to positive. I can't abide by that. Still can't abide by that. I have a hard time PDFing those rows. All right, so y has a local min at x equals 1 because y prime switches from negative to positive. Awesome. Does y have a local max anywhere? No. How do we know? Well, y is guaranteed not to have a local max because if y had a local max, it must occur at a critical value or an endpoint. And we're dealing with an open interval negative infinity to infinity. My exponential function goes on forever in both directions. The only place where y could change direction is at a critical value, and I only had one critical value. So that's the only place where y could change direction, and my sign chart guarantees that. All right, so let's go ahead and tackle our concavity. So which derivative tells us about the concavity of our original function y? Maggie? Double prime, so here we go. We already have y prime. Our y prime expression rewritten is e to the x minus 1, the exponential itself times the derivative of the exponent times the natural log of the base, minus the derivative of x is minus 1. And now we'll go y double prime. So y double prime would be the derivative of y prime. Here we go. The derivative of an exponential function is the exponential function itself times the derivative of the exponent times the natural log of the base, and then minus the derivative of 1 is 0. And so my y double prime expression is just e to the x minus 1. Awesome. My possible points of inflection occur at x values where y double prime equals 0 or is undefined. As we've already discussed, e to the x minus 1 is never undefined. It's defined for all reals. It's just my exponential function shifted over 1 unit to the right. Does y double prime ever equal 0? Well, we could tackle that function behavior-wise. If we think about y equals e to the x, does that ever equal 0? No, in fact, it has a horizontal asymptote as you look to the far left end of the graph, right? Y values approach 0, but never equal 0, and so y double prime will never equal 0. However, if we're trying to show our work here, we could set equal to 0 and see procedurally. If we forgot that, I'm trying to solve this equation, so again, we take the natural log of both sides to get that variable expression x minus 1 down out of the exponent. So when I do so, I get ln of e to the x minus 1 is x minus 1, but on the right I get ln of 0. When I see ln of 0, I say, wait, I can do that. What's ln of 0? Undefined, and so there are no values of x. We get an equation that is never true. That's undefined. That just means that there's no values of x for which y double prime equals 0. So no possible points of inflection. Does that mean y doesn't have any concavity? No, it just means that y doesn't switch concavity anywhere along it. It means that we don't change curvature anywhere. We still can determine the intervals of concavity and which curvature, either concave up or concave down, y is by making a y double prime number line. So we'll still make a y double prime number line. It's just we won't have any critical values on it. For all x, y double prime is what sign? Well, let's plug in any x value. I'm going to plug in 2. When I plug in 2 to my y double prime expression, I get e to the 2 minus 1 is 1, is e to the first is e is about 2.7. Is that positive or negative? Positive, indicating that y double prime is positive for all values of x, which means that y is what? Concave up for all values of x. So, to answer the original question, y is concave up for all x in the domain that is negative infinity to infinity, because, you guessed it, y double prime is positive for all x. Awesome! I can't wait to see what this looks like. Are you guys excited? I'm excited. So let's go ahead and see if we can't make our XY t-chart to get some points. And again, no, I don't have any scale label on here because we're going qualitative. We're not being exact quantitative in terms of the zeros of the function or anything like that, but we do want to be qualitatively correct with my curvature, where my local extrema occur, and so on and so forth. And so let's go ahead and make a number line here. I'm sorry, an XY t-chart. And on our XY chart, we want to pick our critical values and then maybe an X value that's convenient on either side and see what we can do. So we had X equals 1, and that's it. So that's not very much to work with. So I'll go ahead and pick 1, and maybe I'll pick 0. And I'll leave a little space just in case we want to add more to that. And then I'll go ahead and pick 2. Alright, so if I plugged in 0 to my original function and evaluated it, I get e to the 0 minus 1 is e to the negative 1 is 1 over e minus 0 is 1 over e. So 1 over e, again, this is exact, right? 1 over e is exact. But that's about 1 over 2.7, right? 1 over 2.7, so that's about 0.3. So about 0.3, I don't know. Let's plug in x equals 1 to my original. Again, we're doing this non-calculator, so we gotta see how well we can do. E to the 1 minus 1 is e to the 0. E to the 0 is 1, yes? So 1 minus 1 equals 0. So it looks to me like our local minimum at x equals 1 is 0. Did I do that right? E to the 1 minus 1 is, e to the 0 is 1 minus 1 is 0. So this is a local min. Awesome. And x equals 2 into my original function. E to the 2 minus 1 is e to the first is e minus 2 is e minus 2. So exactly e minus 2. E minus 2 would be about 2.71828. So 2.7 minus 2 is about 0.7. All right. So I'm going to go ahead and go just maybe 1, 2 and a half, 1, 2 and a half, 0.3, 0.7. So 1, 2, 1, 2. Woo! All right, you guys ready? Let's go for it. I'm feeling good about this. I have no idea what this looks like though. So 0, 0. So at x equals 0, we have a regular function value. It's not a point of inflection. It's not a local max or min. It's just a data point to help us with our sketch. So at x equals 0, we're at about 0.3. So that would be about here. Yeah? At x equals 1, we have a local minimum. So we're changing we're changing direction there, switching from decreasing to increasing. At x equals 1, comma 0 is a local minimum. At x equals 2, y equals about 0.7. So I'm going to go ahead and include that here, and that's about here. Yes? All right. So now when I go ahead and make my graph, I want decreasing until x equals 1, increasing afterwards, and I want concave up all throughout, right? Concave up all throughout. Yes? Yes? Okay. Can we do that? Yeah, we can. We just want a right side up bowl shape, it looks like. Right side up bowl shape. So I'm coming in, horizontal tangent. I don't know. That satisfies all our stuff, right? We've got right side up bowl shape. We've got decreasing, we've got increasing afterwards. All right, moment of truth. Let's see how we did. So I'm going to change my window to match it. Let's do a window of, I'd say about negative 2.5 to 2.5, because we're trying to see how well we did. Y min, negative 2 to positive 2. Maybe? Yeah? Maybe? Our y equals, we need new functions, so clear out that polynomial. We need an exponential e to the, up in the exponent we need x minus 1 all up in the exponent. Out of the exponent, ground floor minus x. Is that right? So e to the x minus 1, close exponent minus x, and survey says, take a big deep breath, shake it out, moment of truth. Pretty good. Pretty good. Hey, we did it without a calculator, with ease, right? With exponential transcendental function, that's pretty cool, with ease. Because like it was easy, but also with exponential ease, basically.
Not fun.
Whatever. You're funny. You're funny, Brandon. Oh, guys, we're killing it. So let's go ahead now. We've taken a look at a transcendental. We've taken a look at a polynomial. Let's do an algebraic one. So let's go ahead and take a look at a radical. Again, non-calculator. We're going to go ahead and consider and investigate through analytical means the graph of y equals x minus 3 cube root of x. And so on our test, you're going to have to deal with some algebraic functions that may include radicals. And so we have to be comfortable with dealing with those and finding critical values, crossing points, inflection, intervals, and concavity, and the like. So here we go. We know our first derivative y prime tells us about increasing versus decreasing behavior. We just now have an algebraic function, so let's be careful with our derivatives. Here we go. I know y prime would be given by term differentiation yields 1 minus 3, and here we go. X, right, to the 1/3 could be a power representation of the cube root of x. And so when I differentiate that, I'm thinking in my head, what's the derivative of x to the 1/3? And I know that would be exponent times the base, so 1/3 times x to the 1 less. 1 less than 1/3 is negative 2/3 times the derivative of the base. It's just a base x, so the derivative of the base is just 1. So it looks like my derivative is 1 minus 3 times a third times x to the negative 2/3. And if I want to be finding where y prime is undefined or when it equals 0, I'm going to rewrite this to make it prettier. So my y prime I'm going to rewrite as 1 minus, and 3 times a third is just 1, and x to the negative 2/3 is the same as 1 over x to the positive 2/3. Yes? Next, I was given a radical notation there. I think it's going to be easier to interpret in radical notation, so I'm going to go ahead and rewrite yet again and change that x to the 2/3 on the bottom as the cube root of x squared. So I'm going to go ahead and rewrite again. 1 minus, and I'm going to make that fraction 1 over the cube root of x squared. And lastly, it's much easier to perform my to find my critical values, that is where y prime equals 0 or is undefined, if I can write that as a single fraction. Thanks for making sure your cell phones and electronic devices are off in a way so they don't disturb us as we investigate calculus graphs analytically. So I'm going to rewrite this as a single fraction. Yes, another rewrite. So what do we want to do when we combine the sum or difference into a single fraction? Well, we need a common denominator. And so that first term 1, I'm going to go ahead and multiply top and bottom by cube root of x squared, right? So cube root of x squared over cube root of x squared minus 1 over cube root of x squared gives me my final expression for y prime. By rewriting this as a single fraction, right, it's going to be easier to perform my analysis. I know my single fraction will equal 0 when the numerator equals 0, and will be undefined when the denominator equals 0. That's why I'm rewriting y prime so many times, because it's going to make my critical value generation so much easier. Here we go. I get cube root of x squared minus 1 all over, go gadget arm, cube root of x squared. I know that y prime is 0 when the numerator equals 0, and y prime is undefined when the denominator equals 0. If I can find any x values that create those two situations, then they're critical values, and I must include them in my y prime sign chart for analysis. So here we go. Where is y prime undefined? Well, y prime is undefined when the bottom equals 0. So if the cube root of x squared ever equals 0, then that's going to be a critical value too. So y prime is undefined when x equals what? 0, right? When x equals 0, then the denominator would equal 0, which means y prime is undefined. So it looks like I've got a critical value at x equals 0. Because y prime is undefined. Will my top ever equal 0? Yeah. Will the cube root of x squared minus 1 ever equal 0? Yes. I would add over 1 to both sides. Undo cube rooting by cubing, and then undo squaring by square rooting, and I get a couple things. And so let's see. Cube root of x squared minus 1 equal question mark 0. That would be cube root of x squared equals 1. That would be x squared equals 1. Does x squared ever equal 1? Yes, at x equals positive and negative 1. And so we've got two potential critical values down here. And so I've got critical values at x equals 0. Positive 1 and negative 1. All right, so let's go ahead and do our number line. All right, let's go ahead and do our number line. What x values do we need? We need negative 1, 0, and 1. What is a convenient x value on my leftmost subinterval? Well, we're doing a cube root here of x squared, 2/3 power. 2/3 cube root. Maybe if we did 64 would work. 8 might work better though. Can we do 8? Let's do 8. Negative 8, I mean. So let's plug negative 8 into which expression? Well, which expression is going to be easiest to figure out the sign of? I don't know. What if we tried this one? Let's put in negative 8 right here into this first blue expression. So when I do negative 8 here, the cube root of negative 8 is negative 2. Negative 2 squared is positive 4. I get 1 minus 1 over 4 is 1 minus 1/4. Is 1 minus 1/4 positive or negative? Oh, thank goodness. We were able to determine that without a calculator. Oh gosh, what's a convenient value in between negative 1 and 0? Well, again, given that we're dealing with the cube root, let's pick negative 1/8. Yes, negative 1/8. Negative 1/8 then for x. I'm going to go down to the red radical. It's easier for me to think about this. Negative 1/8 cube root is negative 1/2. Squared is positive 1/4. 1 minus 1 over 1/4 is 1 minus the reciprocal of 1/4 is 1 minus 4. 1 minus 4 is positive or negative. Oh, non-calculator. Crushing it. We need a can crusher on the door on the way out. Pencil sharpener? Nope, can crusher. Because you guys are crushing it every time. It's like checking in and checking out a calculus. When we go in here, we crush it. No, crushing it. And a convenient value to the right of x equals 0, but before x equals 1, I'm going positive 1/8 now. So positive 1/8, cube root of 1/2, squared 1/4, 1 minus 1 over 1/4, 1 minus reciprocal 1/4, 1 minus 4, I get positive, no, I get negative again. 1 minus 4. 1 minus 4 is negative. Are you guys getting that? Negative? Interesting. So I'm getting negative y prime up until x equals 0, negative y prime after x equals 0, right? So I don't have a change in direction there. I wonder what's going on. Do I have a horizontal tangent at y x equals 0? No, where did this critical value come from? Where did that critical value come from? Did it come from y prime equaling 0? No, it came from y prime being undefined. In fact, when x equals 0, my top would be 0 minus 1 is negative over 0 as an infinite form is negative infinity. And so it looks like we've got a slope, right, that's infinite at x equals 0. So we'll see how that shows up on the graph, and we'll use that fact to help us make an accurate sketch qualitatively. All right, one interval to go, you guys. Commuting x value to the right of 1 is positive 8. Positive 8 in for x. Positive 8. Cube root is 2. Squared is 4. 1 minus 1 fourth is positive. Awesome. Finally, we can answer the question that was asked after long last. So, y increasing on negative infinity to negative 1 union 1 to infinity because y prime is positive, y decreasing on negative 1 to 0 union 0 to 1. Why am I not including x equals 0 on my interval of decreasing? Y prime was negative before, y prime was negative after, right? So, did y prime switch, did y switch from decreasing to increasing there? No, and yet I'm choosing to use parentheses there. How come? Well, y prime was undefined there, which means y prime was, in this case we saw infinite, which means what type of feature would y have? But not an asymptote, but still vertical, but not a vertical asymptote, a vertical tangent, a vertical tangent. Remember, a vertical tangent slope is undefined. We can't say whether it's straight up or straight down, and so I'm just going to leave it out here, all right? I'm going to leave it out here on my intervals. What would my because be? Same, because y prime is negative. All right, guys. I'm interested in seeing what this looks like. Let's go ahead and do then our relative extrema. It looks like y has local extrema when y prime changes sign. And so while we had a critical value at x equals 0, it does not contribute to a local max and local min because y prime didn't change sign. It was negative before, y prime was negative after, so there's no local extreme at x equals 0. But there is a local, what feature at x equals negative 1? Local max at x equals negative 1 and local min at x equals positive 1. Let's do it. So, I'm just going to copy that again. Negative 1, 0, 1. And positive, negative, negative, positive. So y has and y has a local min at x equals positive 1 because y prime switches from negative to positive. Oh gosh. So if our y prime is exciting, how about our y double prime? Well, we already differentiated that algebraic expression and generated a doozy. So let's go ahead and see what we want to do for our differentiation here. I think it's going to be easier to go back to our maybe our rational exponent expression here to do our subsequent differentiation. So let's go ahead and import that quickly, you guys. So we had our y, prime was given by 1 minus x to the negative 2/3. Is that right? 1 minus x to the negative 2/3, yes? Okay, let's differentiate that to get our y double prime. So here we go. Y double prime equals term by term differentiation yields the derivative of 1 is 0 minus derivative of power function is the exponential itself. I'm sorry, the derivative of power function is the exponent times the base raised to 1 less. What's 1 less than negative 2/3? Negative 5/3, right? Negative 2/3 minus 3/3 is negative 5/3. Negative 5/3. So I've got negative times negative is overall positive. Y double prime equals positive 2/3 x to the negative 5/3. Rewriting my negative exponent as a positive exponent yields 2 over 3x to the positive 5/3. And a final rewrite so that I have radicals and it's easier for me to evaluate without a calculator is constant 2 over 3, and this would be what? As a radical notation, this would be fifth root or cube root? Cube root of x to the fifth, right? And so we could break that up into x squared outside if we wanted to, or sorry, x outside and 2 inside, or we could just do x to the fifth inside. Let's see, I get cube root of x to the fifth. Okay, y has possible points of inflection when y double prime equals 0 or is undefined. Will y double prime ever equal 0? No, the numerator, the only way for a fraction to equal 0 is if the numerator equals 0, and 2 is a positive constant that will never equal 0. So y double prime is never equal to 0. However, y double prime might be undefined. Will that bottom ever equal 0? Yes. For what values of x would the denominator equal 0? 0. So we've got a possible point of inflection at x equals 0. However, we don't know if it's a point of inflection until we do a sign chart with y double prime and see if y double prime switches sign. And so in order for y to have a point of inflection, y double prime must switch sign, indicating that y actually changed curvature and didn't just almost change curvature. So here we go. Y double prime, we'll label every single number line we make. We'll consider the possible point of inflection x values, which come from a single x equals 0. And we'll do a sign analysis to determine the sign of y double prime. Into which form should we plug? Whichever one we want. I'm probably going to do the radical one. So let's pick a convenient x value to the left of 0. This time we can get away with negative 1. Can we just do negative 1 now? Yes? So negative 1 in for x to the fifth is negative 1. Cube root of negative 1 is negative 1. Times 2/3 is negative 2/3. So I'm getting negative. I'm getting negative. X equals 1 would be a convenient x value to the right of, and I'm getting 1 to the fifth is 1, cube root of 1 is 1, is 2/3 is positive, I'm getting positive. So by golly, it looks like we've got y is concave up on 0 to infinity, concave down on negative infinity to 0. All right, so let's answer the original question. Looks like y is concave down on negative infinity until 0 because y double prime is negative and y is concave up on 0 to infinity because y double prime is positive. Oh gosh. Okay. Non-calculator. Can we put it all together? I sure hope so. So again, notice how the scale here, I don't have tick marks on my scale. We're doing qualitatively, but we're gonna do our darndest. So we've got some more things to include now. We've got -1, 0, and 1 were all critical values. And 0 is also, looks like the x-coordinate of the point of inflection. So we need -1, 0, and 1, and we'll choose a convenient x value on either side of that to see if we can't make a good picture. So my original function did have a cube root in it. So again, I think -8 and +8 might be my best x values to choose if I'm doing this on a calculator, and we are. So here we go. I'm going to choose my critical values go on here, so I'm going to put -1, 0, and 1. I'm also going to choose an x value on either side. I'm going to pick -8, because I know how to do the cube root of that, and +8, because I know how to do the cube root of that without a calculator. So let's go ahead and try. Ready? -8 into my original function. Everybody see an x. Evaluate it. I get -8 minus 3 times, what's the cube root of -8? -2. Is that right? So I get -8 plus 6 is -2. Are you guys getting a -2? -2? Hey, that wasn't so bad. I mean, the beginning was kind of touch and go, but I think we worked it out at the end. I got a nice integer response, so that's good. -1 is the original. So I get -1 minus 3 times, what's the cube root of -1? -1. So I get -1 plus 3 is +2. +2, we know to be, right, then, would be a, what feature? X equals -1, we have a local, a relative maximum. This is a local max. I got this one. X equals 0 produces y coordinate of 0. What's going on here? This is an inflection point. How do we know? Y double prime change sign at x equals 0, indicating y changing curvature at x equals 0. Therefore, there's an inflection point at x equals 0, and the point is 0, 0. X equals 1. Here we go. 1 minus 3 times 1 is 1 minus 3 is -2. Yes, -2. And 1 to go, 8. Minus 3 times cube root of 8 is 2. 8 minus 6 is 2. So what happened when we labeled at x equals 1? Isn't there a key feature? Yes, there's a local minimum at x equals 1, and the y coordinate was -2. So this is, right, this is a local minimum. Yeah, local minimum. Awesome. Gosh darn it. Getting psyched, getting pumped. All right, so let's see if we can do this. We go from -8, -8, and these gave us integer points. So I think I'm going to make my x scale, right, to -10, and I'll make my y scale, though I'm not -2, 2, 0, -2, 2. Maybe I'll just go -4 to 4. Yeah, -4 to 4. So let's see if we can't do that. Don't like it already. Too big. Yeah, okay. Y scale, we need to get released to it. So I'm just going to do 4 probably. Nerves. -8, -2. -8, -2 would be what here? Pretty good? Column? For front rower. and -1, 2 is here, and 0, 0 is here, and that's a point of inflection, and 1, -2 is here, and 8, 2 is here. Yeah, about. I can't tell when it's close. Alright guys, what do you have to do? Well, I still need my concavity. We're going to try to put that. So what? Concave down till 0, concave up. And max, infinite, min. Okay. Can we do it? Can we do it? That's not the Bob the Builder response that I was hoping for. Can we go to? Yes, we can, right? Yes, we can.
Give it a shot.
Here we go.
Oh, yeah, I think so.
Concave down, vertical tangent, local min, concave up. Ah, gosh darn it, that's tough, but I can't wait to see. Okay, let's go ahead and see what our grapher says. So I'm going to clear out that business, and we need to make the same window if we're going to try and recreate this. And so I went -10 to 10. Let's everybody check. Come on, this is our culminating graph here. So y min will go, what did I do, -4 to 4. Oh, getting a little nervous. It's all right. Stay strong. X minus 3 cube root of x. I don't want to steal your puzzle. Did you check? Is it okay? You're waiting for me to check? I'm not hearing any oohs or ahs. That means you must not have done it because, or we did it wrong. I hope we didn't do it wrong. I felt really good about it. There's 2, yeah. Oh my gosh! Ooh, ah. I'm feeling pretty good about that, guys. So we've seen how we can use calculus, right, to qualitatively sketch a graph analytically without the use of a graphing calculator, and that's powerful. We have all of our key features like local extrema, dictated points of inflection. We've shown clearly our curvature, and we've done it without our graphing calculator, which up until now has been our security blanket. I have to admit, though, I really enjoyed checking on the grapher to see how we did. So that's pretty powerful. We made this graph without once going to the graphing calculator, and we only did it at the end to check. And so that's powerful, and that's pretty cool. All right. What we're going to do is hold off on our 8.2 until day 2b. What? Yes, I made a day 2b up. Because this is so important, right? The behavior of y as dictated by its first and second derivatives is so important, and occurs on multiple choice. For your response every single year. We're going to go ahead and do another day 2b, and we're going to use our 8.2 sheet. We're going to hold off on that until next time, and so I didn't include it for your pickup. But we are going to go ahead and take care of our closure. So while we'll hold off on this stuff, we are going to close up for the day. And so nice job. Let's go ahead and have a written response that you're ready to share with the entire class. How does one determine the relative extrema of a function using calculus? How does one determine the intervals of concavity using calculus? And must one construct a y-prime number line to determine the absolute extrema on an interval? That I'm going to hold off on because that is the second derivative test that I kept deleting, right? Every one. I kept deleting it at the end, and so I'm going to go ahead and delete this last one. And we're just going to do these 2 main things for our discussion today. And then when we have our 2b, since I stretched it and made it a 2b day, we can go ahead and include that second derivative test then. Awesome. Okay, ladies and gentlemen, what's our general strategy then to determine the relative extrema of a function using calculus? So what do we do to determine relative extrema? What is it that we did procedurally? Grace?
Formula and y prime changes signs.
Absolutely. We know that y is going to have a relative extreme when y prime changes sign. And so we'll take y prime, get critical values, construct a y prime number line, and see when y prime changes sign. Absolutely. I'm going to say that in 2 steps. We're going to see where y prime equals 0 or is undefined. Make y prime number line and perform sign test to see where y prime changes sign. That was the point. Good job, Grace. Y prime changes sign is where we have our local extreme. How does one determine the intervals of concavity using calculus? So what do we do for intervals of concavity? Courtney?
It's like the sine of the y double prime.
Absolutely. And so we basically do the same thing, right? We basically do the same thing. How much of this can I get? I bet I could get a lot of it. Except we're going to see where y double prime equals 0 or is undefined. Those will give us our x values for possible points of inflection. And then we'll make a y double prime number line, perform a sign test, and see where y double prime changes sign. And the sign, we don't have to see where it changes sign, we just need to see what the sign is. Absolutely. Great work, you guys.